This is a very interesting problem. It's a college algebra problem or algebra problem using exponential functions. So I don't know if you've ever read books or watched movies and hear people make mathematical claims. Well, Michael Crichton made a mathematical claim here in his book, and we are going to see if he's right. So he's talking about the uncontrolled geometric growth of E. coli. And this here is a quote taken from his best-selling book called The Andromeda Strain. I don't know if I'm saying that right. I'm not worried about it. So it says here, the mathematics of uncontrolled growth are frightening. A single cell of bacteria would, under ideal circumstances, divide every 20 minutes. Okay, so divide every 20 minutes. That is not particularly disturbing until you think about it, but the fact is that bacteria multiply geometrically. 1 becomes 2, 2 becomes 4, 4 becomes 8. In this way, it can be shown that in a single day, this is his claim, a single day, one cell could produce a super colony equal in the size and weight to the entire planet Earth. Okay, so that's his claim, and we're going to prove if he's right or wrong based on the wonder that is mathematics. Okay, so in class this semester, we decided that every time we create a exponential function, we're going to use a chart. So here's his write an equation, which is going to be exponential. It's going to be of the form y equals ab to the t for the number of E. coli cells present if a single cell of E. coli divides every 20 minutes. So if I build myself a little chart here, this is my time and this is bacteria. And initially he says I have one cell. And then after 20 minutes, I should have 2 cells. So taking notes here, this is going to be in terms of minutes and this is bacteria. So my formula will be B equals a little b to the t. Capital B being bacteria, t being time, capital A and little b are constants. We know capital A, that's our initial value, so that's going to be 1. Then to find B, I'm going to use this ordered pair. So I will have 2 bacteria after 20 minutes. Now, I always put that 1 there, and it's mostly just to remind me what my initial value is. Solving for B, 2 equals B to the 20th. B is equal to the 20th root of 2. And if we put that in our calculator, again, I don't like radicals if you have been watching my videos, but I can take 2 to the 20th root of 2 the exact same way as typing in this way. 1.0353. 1.0353. So then my final equation turns out to be my number of bacteria is equal to 1 times 1.0353 to the t. Now here's where we're going to prove, next is where we're going to prove whether or not Michael Crichton is right. How many E. coli would there be at the end of 24 hours? Well, 24 hours isn't minutes. So if I want to change 24 hours into minutes, I need to see 1 hour. I have 60 minutes. So that's going to give me 1,440 minutes. That's what I'm going to use in my formula. So B equals 1 times 1.0353 raised to the 1440. And that means the number of bacteria that I end up with, 1.0353 raised to the 1440, 4.9585, 4.9585 times 10 to the 21. So that's how many E. coli bacteria I'll have at the end of 24 hours. Now remember, this Michael Crichton guy, he's comparing weight. He says equal in weight of the entire Earth. Well, weight is different than mass. We're actually going to compare the mass of the bacteria versus the mass of the Earth. So if I come down here, we have the information that the mass of an E. coli bacteria is Sorry. Sorry. The mass of an E. coli bacteria is 1.7 times 10 to the minus 12 grams. The mass of the Earth is 6.0 times 10 to the 27 grams. So we're going to figure out compare masses. Now, if this is how many bacteria I have, and each one of those is this many grams, I just have to multiply the two to determine how many grams I have after 24 hours. So we want to determine if the claim that he makes is accurate. So 4.9585 times 10 to the 21 times 1.7 times 10 to the minus 12 gives me 4.9585 times 10 to the 21 times 1.7 times 10 to the minus 12. Well, I have some little bit of math sense here, and I'm pretty sure that this isn't going to be 6 times 10 to the 27. Just based on these powers here, this is 21 power, that's minus 12. That's not even close to 27. So I'm getting 842945 with 4 zeros. 842945 and 4 zeros. So that's a pretty big number. And I know, I'm sorry, I wrote that crookedly. Put that in scientific notation. That's 8.4295 times 10 to the 9th, which is definitely not the mass of the Earth. So is the claim accurate? No. But the next part says, approximate the number of hours we should have allowed for the statement to be correct. So instead of saying 1 day, what should have Michael Crichton said? So calculate hours to get 6.0 times 10 to the 27 grams of E. coli. So to do that, I can't really use this formula straight away because this is just number of bacteria. But if each of these bacteria B weighs 1.7 times 10 to the minus 12, if I want the weight, I just multiply that number on both sides, and I have adjusted my formula to work for the, not necessarily the weight, but the mass. So if I come down here and adjust my formula, then the mass of bacteria I will get is equal to 1.7 times 10 to the minus 12 times 1.0353 to the t. Now remember, this is mass of bacteria. Mass. That's why this is changed to m, where m is equal to 1.7 times 10 to the negative 12 times b, the original capital B. Okay. Now I want the hours to get this many, so that means my mass is going to be 6.0 times 10 to the 27. So I'm going to give myself a little room and start writing over here. 6.0 times 10 to the 27 is equal to 1.7 times 10 to the minus 12, 1.0353 to the t, solving for t. And again, these are just numbers. The only variable I have is this t here. So I'm going to use logarithms and do the same thing I always do. So I'm going to divide both sides by that number. I'm going to try to avoid using my calculator till the end. And even though this is going to look messy, it doesn't matter. Just keep a good track of it and you should be fine. So I divided both sides by that number. Now I'm going to take the natural log and use the power rule. Natural log of both sides. When I use the natural log here, I'm going to bring down the t. That's what the natural log, the whole point of it is for. Removing that t from the power. Now to isolate the t some more, I'm going to divide both sides by this natural log. So I'm going to come over here to do that. So the exact value for t, natural log of 6.0 times 10 to the 27 divided by 1.7 times 10 to the minus 12 over the natural log of 1.0353. Now, time here, I didn't adjust time to be hours, so this is actually minutes. So in the end, I have to convert this to hours. But let's see what this is approximated in minutes first. My trusty calculator. So I have to make sure that these numbers, when I enter them into the calculator, are all in parentheses, these two numbers right here, in order for the order of operations to work. So it's natural log of parentheses 6.0 times 10 to the 27 divided by 1.7 times 10 to the minus 12. Now that parenthesis there is to close off that parenthesis there. So that closes out that one, closes off that guy, that closes off that one. And then I'm going to divide by the natural log of 1.0353. See what number I get. So it turns out that t is 2624.9264 minutes. And now I want to convert that to hours. So in 1 hour, there is 60 minutes. So that means I need to divide this number by 60. And I'm getting t equals 43.7488 hours. Now that's less than 2 days. If you want to know how many days it is, you divide by 24. There's 24 hours in a day. So you get t is approximately 1.8229 days. Now, that's still pretty scary. In less than 2 days, that E. coli breeds to having the same mass as the Earth. So it's still frightening in a sense that bacteria out of control can grow that fast.